All right, so today is chapter 14 time, and I honestly don't know how long it's going to take. We might be able to finish this today or at least get close to the end. This is just one of those chapters where I am going to give you a bunch of cool facts, and it's not a lot of like you play around and notice things. It's just like I'm going to show you the cool facts, we'll see them together, and go from there. But I do have a few things that you can play around with. But yeah, this is chapter 14. There's a lot of important things to talk about. Please read that one after you finish chapter 13. But yeah, the title is, as you would expect, we're going to talk about averages today. And like, why is it so important to care about them? We love them, right? We love averages. We love calculating them. But let's get very, very comfortable. So the other word for average, the fancy statistical word, is mean. And it tells you something nice about the data that you have. So let's say that this is our hard collected data. We've got some integers, 2, 3, 3, and 9. So that's all the data we've got. We can calculate the average quite easily, right? We add them up, we divide by how many, and it's apparently 4.25. So some things to notice. If our data was whole numbers only, the average does not have to even be a whole number. First of all, it could be something outside, or some float value if we're dealing with Python. It doesn't have to be a value. The average does not have to have appeared anywhere in the sequence. It's just a brand new value that's kind of like in the middle in a certain sense, right? And it doesn't have to be an integer, even if your data were integers. But it's guaranteed to be somewhere between 2 and 9, right? Your average can't be outside of that because it's supposed to mean somewhere in the middle, all right? So your average or your mean is going to be between the minimum and the maximum, but it doesn't have to be halfway in between because some numbers may pull it one way versus another. You can see, like, if you graph on our elementary school number line, what in the world, where are we? I guess I want arrows, not those. My best rendition. Like, where's 2? If this is 2, 3, 4, 5, 6, 7, 8, 9. The average was 4.25, so it was there of all our numbers. It was not smack dab in the middle of 2 and 9, was it? So it didn't have to be. This extra 3 here and this other 3 here kind of pulled it more to the left, didn't it? You can think of it that way. It was pulled to the left by these small numbers between the 2 and the 9. So the 2 is the minimum and the 9 is the maximum. It was not in the middle, all right? So it's like, it's going that way. Though the units of average, if these were like, I don't know, what could be a whole number, like the number of heads when you flipped a coin or something, the average is still the same unit. So it's still like, on average, we got 4.25 heads when we flipped our coins. So it's the same kind of unit. It's not like something square, like when you know that when you do some things like density calculations, you've got some weird units involved, but it all just kind of cancels itself back out. You're back at the same units. So whatever you were using. Yeah, let me show that to you. Wait, do I want to do something else? We'll get there after a question. I want you guys to try this. Just think about it. You don't have to write it down anywhere, but we'll discuss this in a second. Remember that there's also a concept of a median. All right, so the median of this distribution, 2, 3, 3, 9, is the number right in the middle, which is 3, isn't it? You take the average of 3 and 3, which happens to be still 3. So the median would be 3 while the average was 4.25. Let's write that somewhere. I don't know. Median of these numbers is 3. So that is a value in the collection, isn't it? Usually, at least. So thinking about that, let's talk about it. So here are 2 histograms of some data. Are the medians of these distributions that are talked about here? The only difference is this 10 way up. This kind of got moved to right there, right? So there's some new numbers farther apart, farther out. Are the medians of these distributions the same or different? And are the means of these distributions the same or different? And if you think that they're different, try to discuss with the people sitting next to you which one you think is bigger. All right, so are the medians the same in these 2 distributions? Are the means the same in these distributions? If they aren't, then say which one's the bigger one. Which one has the bigger median / mean? So take a couple of minutes or just a minute, I think, to stare at that, try to guess. You can make up some numbers that might fit that histogram if you want. What do you think? Let's think about that for a second. All right. Any brave souls want to tell me what they think the median is? Same or different?
Median?
Yeah, the median.
It's the same.
Think it's the same? Why?
It's the only difference is that little outlier.
Yeah, these are some numbers, like maybe, I don't know. The numbers used to be like 5. There were 2 5s in this distribution, but now they became like 2 10s or something. But those numbers were way on the right side, and so the middle number was not affected. Yeah. Does that make sense to everybody? So the median is going to be the same. Cool. What about the means? I might have just given it away. But do you see how they're going to be different? Yeah. Which one's the bigger one, of course? The bottom one, yeah. Because these numbers got turned from these to these, they're gonna pull the mean in that direction, just like the 3s of this distribution pulled the mean to the left of the middle. Pulled the mean to the left of the middle between 2 and 9, which is, I don't know, looks about right there in the drawing. It was farther to the left because of those smaller numbers. They were pulling the average down. So yeah, that's how that works. So yeah, the means are different, and the bigger one is that one. All right, does that make sense, Jess? So yeah, that's interesting to think about, that the medians could be the same for these two seemingly different distributions, but the means can immediately change. So the mean is a bit more fickle. I don't know, it deals with more things at once, kind of. So, all right, let's talk about this. So the mean is kind of like where, like if you think of your numbers as a bunch of weights, then the mean is the place where it's going to balance. If you put them on a number line, like I had a large weight at 2, a couple weights at 3, and a weight at 9, and it was going to balance right there, kind of. That's how that was going to work. Does that make sense? That's the answer. So that's how I want you to think about it. And for future me's sake, I'm going to draw these in green to remind myself that this came from another slide. Boop. So I got those guys and that guy right there, and this is where it balanced. That is kind of what the average is doing. That's what the mean is doing. It's the place where the numbers will balance if you think of them as weights. Center of gravity, if you're taking a physics class. So the median, on the other hand, is just like, where is the middle value? All right, it does not really get swayed too much. It's kind of just where's the middle value? It's the 50th percentile, right? And so that's what it looks like. If we zoom in here, hopefully you see it's like median is the middle value. It's like, where do they meet in the middle? And then the mean is, where is it going to balance? If there's like a bunch of big numbers, for example, in this example distribution, like you think that the midpoint is right here or something, the 50% point is right here or something, because there's more numbers on this side. Like there's equal amount right now, but these big numbers kind of push the mean to the right, and it's going to balance more on the right because of that. Okay, zooming back out. So that's interesting to think about. So yeah, if you had a nice looking distribution, like this one, distribution symmetric of out of value. So that if your distribution looked like this, it was beautiful. We're going to study one that looks like this. If it was perfect like this, then both the mean and the median are the same number at that point. If it's symmetric, you're good. It's not going to be pulled. But if it's skewed, the word for like it's not symmetric is it's skewed. It's like pushed in a certain direction. It's pulled. You're tugging it along. The mean is going to be pulled away from the median. If this is the median right there, the mean, like this was the median or something, the mean is going to be pulled a little bit to the right because it was there's some bigger values that are going to tug it along. Okay, so that's the goal. That's the idea. It's interesting to want to then compare means to medians. that would make sense to want to do. Yeah, I think that's kind of what I wanted to say. Do I want to? Yeah, let me just give you an example of that with some data that we've used before. So remember the compensation for everybody in San Francisco in 2019. Let's read that table and we can talk about the means versus the medians. Just to show you data, it was San Francisco 2019, and then all that SF. And there were a bunch of ones where the salary was 0, and those kind of didn't make any sense. So we're going to get rid of those. So where the salary column values are above like $10,000, I actually have real values here. And so there's my San Francisco table. There it is, a bunch of values, and we can do like a histogram of the total compensation. So we do SF dot do a histogram of total compensation, where the bins are these that the book thought were good. NP to A range, starting at 10,000 because that's where we cut it off, go all the way to like 700,000 because that's like one of the highest grossing ones, and go by increments of 25,000. So there's our little histogram, and you can see that it is not very symmetric. There are some very rich people working for San Francisco, like the people doing their investments, that are kind of going to pull the values very large. There's some people, like, you can't even see them on this graph, but they're there, right? Somebody was making close to 700,000. So that means most likely that, like, maybe the midpoint is around here. It's usually close to the highest bin. Like the median's probably around here somewhere, and then the average, the mean, is going to be pulled a little bit that way because of the people that are secretly over here. Okay, so we can look at those. So, dun, dun, dun. We can get the median first. That's the 50th percentile 50 of an array of numbers, and the array that we want is the total compensation part of this table that I've called SF. Column total compensation. So that's how we do it. And yeah, there it is. There's the median. It's like 133-ish thousand. And then the mean, let's actually get this column out and call it something. I'll call it compensation because I need to use it again for the mean. Compensation equals that. So same number, of course. And then if we want the mean, we can do it in a few ways. You can be like compensation dot, I don't think you can do dot average, but you can do dot mean. You can do NP dot average on the compensation array. You could also do NP dot mean on the compensation array. So all those numbers are going to give you back the same thing. Okay, and you can see that it's 138,000 rather than 133,000 for the reasons we talked about. Okay, so the mean has been tugged along in the direction of the chief financial officer. All right, so that's what we see there. Does that make sense to us? Any questions about why that's happening? So the balance point is being pushed along. It's being tugged. Yeah, and so that's useful knowledge to have somebody give you, okay, give me the min, give me the max, give me the average, give me the median. You can kind of infer a lot of things about the distribution with those numbers. All right, so you can't just describe a distribution, first of all, by just giving mins and maxes. For example, like, let me draw a few. Like if there's a bunch of things, you could have some mins and maxes, like these could be your min and max values, like they could exist, but the distribution of the things could look quite different. Like this could be a perfectly symmetric thing. This could be like all over the place. Boop, boop, boop. They still have the same mins and maxes, right? So that's kind of how that would work. It's not the same. If you got the average, that would help, I think. Here's another distribution. Boop. It just like steadily increases or something. Same mins and maxes though. You can imagine you can make those graphs with same mins and maxes, just a bunch of different numbers in between, all right? The average would be helpful. Like the average of this one would be maybe there. The average of this one would be a little more towards the right. The average of this one probably way over here. Or actually, yeah, somewhere in that direction at least. Something like that. The averages would look different. But in addition to the average and the median and all of those, it would also be nice to know, like, how spread out is the data, because what if I gave you this histogram? The mins and the maxes right there. There's the min, there's the max. They're both like that. There was nothing in between. See that? Like the numbers, they just took on one or the other, whereas these ones were kind of sharing things. So like those are a bunch of different options, right? You could have had this one. You could have had this histogram with nothing at all in between, a barren wasteland. So that's interesting. It would be nice to know then, like, how spread out are the values? Because, like, does it look like this? Does it look like this? Does it look like more like this? Min, max, and average and median can't tell you that. I hope you can see that. All right, not too easily at least. Like how close are they? So like think about these distributions. Like you got 0 and 10. 0 and 10. Here's like 0 and 10. Those distributions versus like 4 and 6. Some other distribution where here's 4, here's 6. Those numbers. Do you see how their mean is the same? It's still 5 for both of those distributions. Like the average is still right there for that one. And it's also going to balance right there for the other one. Interesting to think about. But like these two distributions, these two numbers are way different than these two numbers. You see that? So we need some other measure. All right, that's what we're thinking about here. And a good standard way of defining the measure is aptly named. It's called the standard deviation. All right. I think we've heard of this. If we have not yet learned how to calculate it, this word exists, right? When somebody gives you some stats, usually you've seen this word before. It appears there. That's what will tell us how spread out the graph is. It's a great number to have. So the standard deviation, we're going to study that in this chapter. All right. So the standard deviation is a number abbreviated as SD, San Diego. It measures roughly how far the data are spread out from the average. All right, how far are the data from the average usually? All right, so the way that you calculate the standard deviation, it's a little disgusting. All right, it is called if you spell it out, it's the root mean square of deviations from the average, and that is a mouthful. And I'm going to give you a good example. But if you want to calculate this yourself, you do it backwards. First, you take the average, then you look at all the deviations of all the numbers from the average. How far apart are they? Then you square those deviations. Then you take the average of those squared deviations. And then you take the square root to bring it back to the original units. Okay? Did you catch that? So there's like a summation that I could show you here, but it's not really worth it. So yeah, read it backwards. The units are going to be the same because eventually, like you've done a square and then you took the square root, so you went back to the original units. But the squaring kind of gets rid of any negatives and it shows you like a distance calculation in a sense. So it's really good. It's a deviation, right? It's how far away are these numbers from the average. And it's very nice, right? So a cool fact about the standard deviation is that no matter what your distribution looks like, it could have been any of these example ones that I drew. It's always going to be the case that the bulk of your data, just by virtue of the way this number works, the bulk of your data in your distribution are going to be like centered around the average plus or minus a few standard deviations. And we're going to study what that means. Okay. So it's really nice. You can turn all your data sets kind of into one data set based on standard deviations. We can turn it into a different number of units. Like how far away, how many standard deviations is this value? How many standard deviations away from the average is this value? You can turn every data set into one that could be defined like that. It'll look that way, okay? So that's a lot of words. Can I show you an example of how to calculate it? Are there any questions before I do that? I think that's probably what you want. All right, so let's say, again, standard deviation, root mean square of deviations from the average. All right, so let's spell it out. Let's do a slope. So let's take these numbers. Let's calculate their standard deviation. I'm going to do it in stages in Python so that you have each step. All right, so I'm going to copy these numbers. I've sorted them for our benefit, but they didn't have to be sorted. It's just a bunch of numbers. That's your data set. And so here are our nums. Make an array of them. So there they are. I got them. So we can the first thing we do is we're going to calculate the average. We need that first. All right, so first we need the average. So it is... call that the mean, right? np.mean of our nums. So that's our average. It's called mean. It's 4. The average of these numbers is 4 because there's more smaller ones than bigger ones between 0 and 9. It's like a little bit. It's like 4.5 is smack dab in the middle of 0 and 9, right? 4 is the mean. It's been tugged towards the left. There's more, like the 3's are duplicated. Yeah, so that's the mean. And so we've got that. And now we want to, for every number now, calculate how far away it is from the mean. That's called the deviation from the mean. How far does it deviate? And so we want to take every one of our numbers. The NumPy library makes this easy on us. Take every one of our numbers and calculate how far away is it from the mean. You could say nums minus mean or mean minus nums, doesn't matter. But like here's how far away all the numbers are from the mean. 0 is -4 away from the mean. 9 is 5 away from the mean. So you got negatives and positive numbers, but these are our deviations. Does that make sense to us? How far away is each number from the mean? You could have done it differently. You could have done mean minus nums because we're about to square it. Doesn't matter. All right, so these are our deviations. How far away is every number from, how far away is every num in our data set from the mean? That's what a deviation tells us. And so I'll just make a table with those to make it clear. So let's make a table with columns. We've got each original value, that's our nums. And then we've got the deviations, deviation from average. And that's deviations. So here's what we've done so far. Here's our original values, and here we've calculated that the average is 4. Here is each number, the deviation from the averages. It's 4 in the negative direction for the 0, and it's 5 in the positive direction away from 4 for the 9. Okay? So those are our deviations. And yeah, let's call this table something so I can add more to it later. These are our calculation steps. You could have done this faster without making tables and things, but it's worth showing. Okay, so there's our table. And so then we're going to take we're going to square the deviations. Wait, yeah, we're going to square the deviations next and then take the average. Let me show you why we want to square them. We can't just immediately take the average of the deviations because we actually get nothing useful. Watch. The sum of the deviations, and I hope this becomes intuitive, is 0. Because the average is in the middle, it's the middle number, the sum of all of our deviations from the average must kind of necessarily be 0. I hope that makes at least a little bit of intuitive sense because the average was in the middle. How far away is each of these from the average? If it was in the middle, like the big things cancel out the small things. That's the whole point of being an average. So the sum of all of our deviations is 0, which means if we were to take the average of that, because the average of the deviations would involve summing them up and then dividing by the size, it would still be 0. So in order to like have something normal, we kind of want to turn these negatives into positives, and one way we can do that is the absolute value. The other way is squaring them, and it's more cool and mathematical. We get cooler properties if we square them. All right, so we're going to square our deviations so that we can actually take the average of them and we get some non-zero number. All right, it tells us something interesting. So yeah, we're going to square our deviations. So that's just deviations star 2. We square them all. This is what they are. Okay, so those are our squared deviations. Is that? And then we can add that to our calculation steps. Dun, dun, dun. Calculation steps with another column with our squared deviations now. Squared deviations from the average. And that's the squared deviations. All right. There, so this is the steps so far. We got our original values, we found the average, we calculated the deviation of each value from the average, and then we've squared those deviations. And then we take the average of those squared deviations, all right? So we take the mean now, we're on the mean step, right? So we take the average of our squared deviations, np.mean, squared deviations, and we get this value, all right? The units are now in squared of whatever it was. If these were like amounts of heads when I flipped a coin, this would be squared amounts of heads. So we've taken the unit and we squared it. the average, it's still that same unit, right? So it's squared unit still. And this is almost the end. We have to take the square root to bring it back to the original units, but there's a word for this step. It's called the variance. So that's sometimes a useful number we care about. We've called it, mathematicians have named it the variance. It's got a bunch of sevens. That's lucky for us. And then to bring it back down to the original units, back to just heads of coin flips or whatever, we take the square root. All right, we take the square root. We're finally on the last step, which is the first word. All right, so the square root gives us, as variance, we can do the square root. There's a couple ways to do the square root. It's like there's math dot square root of variance. Yeah, or you could just be like variance to the 0.5. That would also work. All right, and that is our standard deviation. All right, SD for short. There it is. We did not have to go through this arduous journey, but I wanted you to see how it's calculated. There is, of course, a function, np.std. All right, standard deviation in the NumPy library of our original numbers. They're just our nums, right? Gives us the same value. All right, but that is the process. All right, the first thing is get the average, calculate the deviations from the average, square those deviations, take the average of those squared deviations, then take the square root to bring it all back to the same units. Does that make enough sense? Any questions about that? That's how we calculate it. And it's like, all right, this is a spread. It's like a lot of our numbers are just a couple standard deviations away from the average, a couple 2.78s away from the average. And that's honestly true. This is like 4.254 was the average, right? Or something like that. All the numbers are just a couple standard deviations away from that. Not just one, but maybe a couple in one direction or the other. Okay? So yeah, that's how you do it. Your turn. All right? I want you to try this. I guess probably the best thing for me to show you is this. This is how you do it. Using that as your guide, try to use Python. You don't have to make tables or anything. Just like start with the array, get the mean, get the deviations. You can do it by hand if you need to, but see if you can. You can use Python for help, but don't just like cheat. Don't use this yet. Calculate the standard deviation of these numbers. Give it a try and see if you can get it. All right, and then you check your answer. Of course, you can immediately check your answer to see if you got it right. But try. I'll give you a couple minutes to try to calculate the standard deviation so that you can kind of understand it. Calculate the average. The average is going to be probably smaller than it is big. Give that a try. And I'll do it for you. Do like 3 minutes, let's say. It's backwards. You work your way backwards. First the average of these. Get how far they deviate from the average. Square the deviations. Take the average of the squared deviations. And square root. Bring back the original units. Any questions? Remember that the NumPy library is your friend. You can make the array and you can suddenly just like subtract the mean from it. It's the one thing and does that to every element. Very useful. Another few seconds, and then I'll do it too. All right. Let's see. I mean, you can immediately check your answer, but let me do it too. 1, 2, 4, and 42. I want the standard deviation. So these are our nums now. We'll call them nums again. We can get the mean by doing np dot in a million different ways. np dot mean on nums, sure. So apparently 12.25 is the mean of these numbers. Mean. The deviations from the mean is just like nums minus mean. There they all are. There are deviations. We can square those deviations, right? Because that's the next step. Square them. I can do this all in one step, kind of. Boop, boop, square just like that. So do a couple things at once. Square them. Then we want the average of those, right? Take the average of those squared deviations, np.mean on that. Yeah. And then you square root that. And if I didn't skip a step, that is the answer. So we got the average. We took the deviations from the average right there. We squared the deviations. We took the average of the squared deviations. There's that. And then we took the square root of that answer. There it is. Cool. The world is good. Any questions about that? So that's how you calculate the number. We still need to learn how to interpret it. Okay, are we ready for that? It's a good number. It's useful to have. All right, so let's see. It really does put every single distribution that you could ever have on an even playing field, because you can always turn it into what are called standard units. You can turn any number that you had into just like how many standard deviations was this particular value in my data set above the average. You can turn it into that, and those are called standard units. Another word is called the z-score. I have no idea why it's a z. It has nothing to do with standard deviation. But everybody likes z for that. So yeah, the z value for you turn your value into standard units, the z-score, is you take your value, you subtract the average, see how far away it was from the average, and then you divide by the standard deviation. Like how many standard deviations was this value above or below the average? So if it was negative, of course, that means it was below the average. If it was positive, that means it's above because of the way we're doing the subtraction. And that also means that if your value's z-score was 0, that means it was exactly equal to the average. It was right in the middle as far as the average is concerned, okay? And that just like puts everybody on an even playing field, because when you have a distribution then, and you put it in standard units, here's your distribution, it's now centered at 0 because 0 is your average. It's centered at 0 because that becomes the z-score for the average minus average. And then your standard deviation is like 1 away, and so like that's 1 standard deviation away, that's like 2 standard deviations away, that's the z-score of 1, 2, -1, -2. Like it'll make most of your graphs, they don't have to look like this, but like they'll be as spaced out around about like that, okay? So that's kind of neat. You can turn anybody into this, use standard units. So for example, this 42 value, let's turn that into standard units really quick. 42 minus the mean is 29.75 divided by the standard deviation, which was, I guess, this. The 42 was 1.73 standard deviations above the mean. Does that make sense? So 42 was 1.73 standard deviations above the mean. That's how you calculate it. And so that's a z-score. All right, that's standard units. And so let's do that for like a data set. I think that would be great. Standard units. It's very useful to go to these because then every data set looks the same at that point, kind of. So let's go back to a fun data set that we had where it was like the heights of the mother and the father and then the height of the child. I think it was sons only. So table, read table. It was data. It's called sons heights.csv. We have that. So here's our heights table. We got, I guess it's in inches. So the father's height, the mother's height, and then the height of their son. Could be multiple sons maybe. So let's figure this out. Let's get the averages. Let's get the standard deviations. Let's deal with the height of the sons. All right. So what's the average son height here? It's np.mean on heights column 0, 1, 2. I guess I could just say son, but for fun. There it is. There's the average height is about 70.5 inches. That's the mean height. Boop. And then let's also get the standard deviation of the height. I'll call it SD height. Just np.s standard, std. So that's about 2.55 inches standard deviation. It's not that much. So now let's look at these heights of these sons. Let's do heights.select out just the sun. There's just the sun's heights. It's that part of the table, and we'll sort them. Sort by column 0. So it looks like the smallest, the shortest sun of all the data set, there's about almost 200 of them, was 63 inches. How far away is that from the mean? What's the z-score? What is that number in standard units? It's the value minus the average over the standard deviation. So it's 63 minus the average height, mean height, over the standard deviation. It's how many away was it? It's like the most extreme value, the minimum value in our data set, was about 3 standard deviations below the mean. Almost. All right, so it's about 3 standard. That was the most extreme value we had. At least in that direction. This was about 3 standard deviations below the mean. All right, so that's like our most extreme value. Most of them are not that extreme, but like that's a z-score. That's turning it into standard units. All right, let's do the same for the for the tallest sun in our data set. So let's sort let's do descending equals true. So it looks like the tallest sun was 79 inches. All right, let's do the same for that one. 79 inches. What's the z-score for that? Again, it's the value minus the average divided by the standard deviation. How far away was it? How many standard deviations above or below the average was it? It was a little over 3. All right, so again, this is about 3 standard deviations above the mean this time. And that is a pattern, all right, above the mean. That is a pattern that rings true. It's quite nice, all right? You're never going to find much more than that. I guess I want to show you that right now. Dun, dun, dun. We'll get there in a second. No, I'll do this first. We'll do this first. So we're just talking about standard units. Let's turn every sun height into standard units. Like this was the most extreme in the positive direction. It's about 3 standard deviations above the mean, 3 standard deviations below the mean for this sun. And let's do it all. Let's make a function then that we could like turn everything, like take an array, give back that array in standard units. All right. Standard units. You give me a bunch of numbers, an array of numbers array, let's say, and I will return back to you that numbers array where every number has been turned into its standard units form. So that's like take every number, take every value, subtract the average from it. So let's take the array itself, subtract the average, np.mean of that array, because NumPy lets you do that. Like that's every number minus its average. Now we can divide it by the standard deviation as well of the numbers array. So like that's taking an array and turning it into an array that's in standard units. So here's what we can do now. Let's take the let's do the standard units. Like here is the heights dot column Here's the sun's heights, all of them. We could take that, we can call standard units on that. Here are all the values in terms of how many standard deviations away from the mean are they. These values are in standard units now, we say. And so you see that there's not, a lot of them are just close to 0. They're close to the average. Some of them are like 1, 2 standard deviations away, but no more than 3, it seems. And there's a pattern there for sure. So that's like, let's turn this into a new heights table. So heights equals heights with a new column called sun in standard units. And it's going to be this thing. And that's our heights table now. All right, cool. Follow another sun. So each of these values, instead of 71, you can treat it like this: a z-score, a standard unit, all right, value. So this one was 0.214 standard deviations above the mean. This one was almost 1 standard deviation below the mean. Okay, does that make sense how we're dealing with those numbers? Those are useful numbers. And so let me prove something to you, that the standard deviation is a useful measure. A good deal of all of the suns are going to be within a couple standard deviations, like just 2. You saw that the extreme values were about 3 standard deviations. Let me show you just 2. Let's calculate all the values that are within 2 standard deviations. So heights values where the column called sun standard units, where all the values are between -2 and +2. You can do that, right? That's all the numbers, all the sun's heights between, in standard units, between 2 standard deviations below the mean and 2 standard deviations above the means. All those values, and we can calculate that within 2 standard deviations. Is that? And so we can see how many of the suns that were in the data set were like that. So it's within 2 standard deviations dot numRows divided by all the people, which was just everybody in the heights table, heights dot numRows. About 95% of all the people were within 2 standard deviations of the mean. That's a useful value. It's telling you how spread out everybody is. Does that make sense? Questions about that? And then within 3, that's pretty much everyone. And that's usually true. Within 3 standard deviations, between -3 and +3 for the z-score, for the standard units values, it's about over 99% of the data are within 3 standard deviations. So that's kind of how you deal with this number. Like, take a couple standard deviations away from the mean, that's where the bulk of your data will lie. So if someone tells you that number, you can use that and understand it. Does that make sense? Or we can use that number, so like, even if we don't have all the data, we can kind of imagine the distribution now better. That's the whole point. All right. And so this, like, within 2 standard deviations of the mean, within 3 standard deviations of the mean, this pattern, 95%, 99%, actually rings true for any data set, for most data sets in the world. All right. I should say most and not every, but for the majority of them, they're going to look like this. If we graph the heights of these suns, let's do a histogram. Let's do a standard units histogram. Why not? That'd be great. Do a histogram of the standard units. Look at them. It looks like this. Let's do some bins. Equals, I don't know, 15. It's kind of symmetric. It's kind of like this. A lot of the distributions you could ever want to see are going to look a whole lot like this. Okay, they're going to look like this, and they've this nice person has drawn a bell curve over it. So you may have read about this or heard about it somewhere else, but a lot of the data sets of the world, anything you could possibly want to measure, it's going to look, when you make a histogram, it's going to look bell-shaped like this, this is apparently what a bell looks like. I just imagine like the Liberty Bell or something. It's going to be like tall in the middle and then fan out on the sides just gracefully. And it's going to taper out. And so if your histogram looks like this, or at least it's close, like even this one, it rings true for this one. It looks close enough. It has something in the middle and it kind of tapers away. If your histogram looks somewhat like this, what can we say about this? This is a bell-shaped curve, all right? We can say that it's like the average is going to be right at the center. That's nice, okay? And then the standard deviation, when you have a bell-shaped curve, it's going to be, if you want to read it off like this, the standard deviation is the distance between the average and the points of inflection on either side. This takes math knowledge. So do you kind of see this is a point of inflection, this is a point of inflection according to what they're saying there. It's just like where it stops, like where it starts curving out the other way, kind of like it was going that way and it kind of like goes out that way now. Like it takes boop, boop. You can imagine like there's a sharper curve there. That's your point of inflection for the graph. Like it was going this way and then now it's going a little bit that way. It's going this way, now it's going more that way. That's a point of inflection. So it's like where that happens is that's one standard deviation. When your graph looks like this, at least, which is kind of useful. You don't ever have to read that off usually, but a lot of the time your data set is going to look like this, especially when you get more data, and that is called the bell curve. The technical term for that is called the normal distribution. Like they thought that was so common. That's what we usually see. That's so normal. That is called the normal distribution. All right, if you haven't heard that before. So this is the standard normal curve in standard units. So like centered around 0, which is the average, and 1 standard deviation away is where the point of inflection lies. And so most of the values are between like a couple standard deviations when you have a data set that obeys this and looks like a bell curve. It will always turn into something like this. Virtually everything is going to be between 3 standard deviations, but I hope you can kind of see what's going on there. All right, can you kind of interpret this graph? Most data sets of the world look like this, especially when you take more data, and so we want to study this. This is called the normal curve, the normal distribution. It is the technical term for a bell-shaped graph, bell curve. Okay, so here are the facts. When you have a data set that looks like this, or at least is very close, honestly, this one's close enough. Here's what happens. First of all, no matter what your distribution looks like, it could look like any of these weird ones that I drew over here. No matter what your distribution looks like, here's what's true about the standard deviation. Here's why you want to care about this number. The bulk of your data are going to be between a few standard deviations. So if your average, if you want to go between like 1 standard deviation from the mean and on each direction, -1 z-score to +1 z-score, for all distributions, at least 0, you don't really learn much when it's not bell-shaped. But if you have any distribution at all, you go ±2 standard deviations, ±3 standard deviations, you get this much data guaranteed to be there. That's the point of a standard deviation. It's telling you how spread out it is, and it's going to work for any distribution. The bulk of your data, even if it's a wonky distribution, almost 90% is going to be about 3 standard deviations away from the mean. That's great. That's great news. So it's a useful number. It's telling you how spread out the data is. It's very, very nice to know. Doesn't matter the distribution, but if you had a normal distribution, if it was bell-shaped, then you get even tighter bounds. Almost all of the data are going to be between the range, the average, ±3 standard deviations, so a z-score of +3 to -3. All right? So if you had a normal distribution, about 68, almost 70%, so over half for sure, of your values are going to be between 1 and -1. So that's these guys, between here and here. Right there, you've got 68%. 68% of all your values are right there. 95% are going to be between, about 95% are going to be between -2 and +2. That's 95%. And then 99.7, okay, is going to be between ±3 standard deviations, so from here to here. So, boop to there, all the way to there, that's going to be 99.73% of your data. It's very unlikely to be any more than that. Just huge outliers at that point. If your data looks like this, that's going to ring true, and that we just saw rung true for our heights. This is close enough to a bell-shaped curve. It worked out. 95% of the data was within 2 standard deviations. 99, almost 0.7, was within 3. So that's going to ring true for most of your data in the real world, which is awesome. It's good news. That is why we want to study this, and why the standard deviation is a very good thing to know. Okay, any questions about that? It's a cool idea, I think. It's a very cool idea. So yeah, this is that all over again. So average plus or minus 2 standard deviations. This is in standard units right now. 95% of your data is going to be between here and here. What it's going to look like. All right. That's good. We care about like a 5% cutoff a lot in statistics, so that's why 2 standard deviations is usually a golden number here. If you would like to calculate like how many values, what's the percentage of the values between like 1.5 standard deviations away from the mean, there's a mathematical function that you can use. This graph is defined in terms of the number e, the magical mathematical constant e, and some other exponents and things. But there is just a function in the library. It's called the normal CDF, which stands for cumulative distribution function, I believe. Yeah, so here it is. It's right there. I didn't have to remember it. The cumulative distribution functions for the normal curve. What you give it, if you want to like calculate something, here's how you do it. You can say, give me the CDF of a value x, and what that will do is it will go and look on the normal curve, and it will give you the area, all like the proportion of values, to the left of a z-score equal to what you gave. So if this is a graph of CDF, I don't know why I'm in green right now. This is the CDF of 1. This is the calculation. It's like, all right, starting here, give me the proportion of values that are here and all the way to the left as well. It's like all the averages, all the values that are between a z-score of negative infinity to positive 1. All right, so that's what it gives you. You can use that to calculate any value. So here is, let me show that to you. So the normal, see if you want like how many values, what's the proportion of values in a normal distribution that are between like 1.5 standard deviations above the mean to negative 1.5 standard deviations below the mean. Normal cumulative distribution function. So if you want to know an exact percentage for a perfectly normal curve, here's what you do. It's you say from, it's another library. It's the SciPy library. It's cute. We import the stats piece of it, and that gives us access to it. It's called stats.norm for normal, and then you say CDF, and then there's 1. So apparently, the proportion of values that are between 1, that have a z-score of 1, all the way to a z-score of anything smaller, that covers about 85%, 84-ish% of all the data in a normal distribution. If you wanted all the values that were 1 or above, what's the proportion of values that are 1 or above your z-score of 1? Bless you.
Thank you.
Then what you do is you calculate the CDF because it's going to add up to 1. The proportion of values adds up to 1. So if you want this part, you just take 1 minus. So you want all this stuff right here. If you want this stuff, this is 1 minus the CDF of 1. Does that make sense? Because if it adds up to 1, like this is all the stuff that's 1, just take 1 minus that, it gives you the rest, everything over here. So 1 minus this, you better believe, is about 16% of stuff that's bigger than 1. 1 to infinity. All right? So my question to you is, with this in mind, I guess, I don't know the best way to show this to you. I'll keep this open maybe. So crushed ice. I'll give you a minute to try this. Try to calculate the exact percentage. There's about 68 or something, right? What do we say? 68%. See the exact percentage. Exact percentage of values between -1 and +1, +1, standard units. Standard deviations from the mean in a normal distribution. All right, so try to use this fact that this is going to give you everything. This is the percentage of values from negative infinity to +1, and then this is the other way. This is the percentage of values from positive 1 to positive infinity, everything other than that. Try to get it between exactly negative 1 and positive 1. Do you kind of see how you might use this? So think about that. The graph is here. If you want to stare at that for a second. It gives you this kind of idea of everything to the left of you, but you can always subtract to get everything to the right of you. And so there's something you could do, okay? See if you can figure it out. I'll give you a minute to try it, and then I'll show you the answer. Think about it. This gives you everything from that number to the left, onwards to negative infinity. If you do some math to get everything between a certain range, like just positive 1 and negative 1, there's a trick involved, but maybe with enough staring you might see it. Because you want to cancel out those infinities, kind of. There's a way. There is a way. Do I have a graph for it? I do not. So kind of the idea is, all right, if this one, here's my normal curve. If this gives me, if CDF of 1 gives me everything from here onwards, right? CDF of 1 gives me all the blue stuff. That's CDF of 1. I want everything between 1 and negative 1. So like this is 0, this is 1, this is negative 1. CDF of 1 gives me the blue stuff. CDF of negative 1 gives me this stuff, the green stuff as well. This is CDF of negative 1. Do you see how these, like CDF of negative 1, like if you add them up, it's double counted, this part? See that? That's the trick. So if you take CDF of 1, that's all of this. If you subtract CDF of negative 1, all that remains is what was between. Do you see that? So that's what we want. That's how you can do it, if you do that subtraction. So take this one, that's everything from negative infinity to 1, subtract away all the stuff, I guess. Subtract away all the stuff from negative 1, negative infinity to negative 1. All that's left in between now is everything between 1 and negative 1. So there's your 68 is 0.3-ish now. That's how you do it. All right, so the exact numbers are these. Between, you got a perfectly normal distribution, it's mathematical. Everything between 1 standard deviation away from the mean, 68.3%. 2 standard deviations is 95.4%. And then 3 standard deviations is going to be, your distribution is never going to look perfectly like this, but like ideally, this is legitimately 99.73 with some zeros. So that's why they said it that way. All right. Any questions about that? So this is just mathematical. This is like optimal. Your distribution is never going to be perfectly like this, but a lot of things in the world will approach this, and so you can use this as guidance. And I guess now is my job to show you that so many things in the world will approach this. There's some math behind it. Let me show you that math. So it's called the central limit theorem. So here's a very, very, very important and cool fact that some very smart people have proved for us. The distribution of the sum or the average of a very large random sample drawn with replacement from a population. If the population is big enough, with replacement doesn't really matter. It will be roughly normal. It will approach normalness, no matter the distribution of the population from which the sample is drawn. No matter what you've got. If you take the average, for example, of numbers drawn with replacement from this distribution, this distribution, this distribution, this distribution, like completely wild distributions, whatever you want, didn't have to look normal. The average value the distribution of that and its spread will become normal. That is a wild and very cool fact. We've actually seen that before in this class with our simulations. But now I can tell you why. It's coming from this idea of the central limit theorem. No matter what, you take a large random sample and you do the average, or you do a sum of values, no matter what the original distribution looked like, the distribution of the sum, bless you, or the distribution of that average that you're calculating is going to look normal. It's going to become normal. And then all the things that we've talked about apply. You know what the spread is. You know how to calculate standard deviations. And also, if you're doing averages, if you're calculating average values, which usually people care a lot about, what your graph is going to look like, what your normal shape distribution is going to look like. The mean is going to center around the original mean for the population, so that doesn't change. And then the standard deviation of the graph that you're trying to make when you're doing an average from another distribution, it's going to be the standard deviation of the original population over the square root of the sample size. So it's going to get a little shrunken usually. The standard deviation is going to be closer together, which is interesting to think about. Let me show that to you. It's very, very nice. It's called the central limit theorem. So I'm gonna prove to you what the central limit theorem holds, just with some examples. Because the math is very complicated. I have not looked into that very well. But let me show you a distribution that is for sure not normal. All the distribution of all the things, like if you're going to roll a die, what's the probability that you're going to get a certain value? So that's this table, right? Table.width column. The value on your die is going to be any value between 1 and 6. 1, 2, 3, 4, 5, and 6. That's my table. I'll call that die. It's one single die as we roll it. The value could be 1 through 6. Okay? What's the probability of you getting a 1? 1/6, right? Probability of you getting a 2 is 1/6. So the distribution of the probabilities is 1/6 all around. So you can make a histogram of that. And this is like, we want to center it perfectly, like our midterm question. You got to be between like -0.5 and 1.5. Something like that. Let's do that. So bins equals np dot a range, or it's just 0.5. 0.5, 6.6, right? Because you want to go and include it. Here's your probability distribution, yeah, for your rolling a die. Everybody's 1/6. So this is for sure not bell-shaped. Yes, it's evil. No, not evil. It's even. So I guess I got Halloween on my brain. So they're all 1/6, all right? Not bell-shaped at all. It's a uniform distribution. That's the word, okay? So no matter, this does not matter, does not phase us. The central limit theorem is going to apply if I'm going to take some averages. Let's say, let me make a function that does what I want to do. So let me roll a few dice, and get their average value. All right, so now I'm calculating an average drawn from this distribution. All right, so average die value, let's call this. And I'll give it a sample size. So somebody can tell me how many do I want to roll? How many dice do you want to roll? Give me that as a sample size parameter. So to get the die values for each of my, to roll that many dice, I can take a sample of my die table. That'll work, right? If I want to roll, here, for example, if I want to roll 10 dice, then I take my die table and I sample it 10 times with replacement. And then here's a bunch of values that were on that dice, on those dice. And I can take the average of that. So that's going to be my trick. So here's my sample. Give me, take my die table, give me a sample of that many, sample size, however many I wanted to be given there, and give back the average. Give back the np.mean of sample column 0. All right, so the average die value when you roll 10 dice, sample size is 10, it's 4 this time, but it's different, it ranges, right? It's random. So that's what I want to do. So let's get a bunch of averages, right? We're drawing from this distribution, this uniform distribution, not at all normal. If I get a bunch of averages, you better believe it's going to become normal, all right? Central limit theorem. So let's roll 1,000 dice, 1,000 times. And you can feel free to play around with these numbers if you want. But let's like you've rolled a bunch of dice, a group of dice. We're going to calculate the average for the group of dice that we've rolled. So let's make an array and keep track of all these values. So for I in np.a range 1000, let's say that my new, or these are group averages, I guess. My next average is just like average die value, roll 1,000 dice, give me the average value. That's my new one, my new group average. Taking the average over a group of numbers. And then I want to add that to group averages. So it becomes itself appended. Append to the end of that this new value called group average. And then we're pretty much set, right? Once we've done that, it'll take just a second, we can make a table with a column that is like the sample, all these sample means, right? Group averages. Here's my big table. A bunch of average values that I got as I rolled 1,000 dice. Excuse me, thank you. Let me take a histogram of that. So with a few bins equals 20 or something. So drum roll, ta-da, normal. Yay, not normal. The original distribution that we sampled from, not normal. We took an average though, after drawing from that distribution, normal. And you better believe if we took more things, more values, it would be even closer to normal. It's still off, but it's real close. All right, so that is the central limit theorem at work. It's wonderful. That's really cool. And we can do, I can prove to you that this is true as well, this like standard deviation calculation of that, because what was the original population standard deviation of the die table? Like what's the standard deviation of the numbers from 1 to 6? We can calculate that's our population standard deviation equals np dot standard deviation of die column 0. So the standard deviation of the numbers 1 through 6. That's our original population standard deviation. It's 1.71-ish. And the standard deviation of our means is apparently going to be this. It's going to approach this. Our population standard deviation divided by the square root of the sample size, which was 1,000. This is going to be even smaller. So it's ideally going to be that. What was, so yeah, this is like our ideal theoretical standard deviation for the mean. So this is NP standard deviation of group averages. I can prove this to us. So it's that. This was the real one. It was like empirical. And this is, here's the theoretical one. It's supposed to approach this population standard deviation over the square root of the sample size, which was 1,000. Empiric. This was like theoretical. That's not that far off. So it really does hold. That's nice. And let's play around with this. Let's make a function that does this for different sample sizes. So I'll call it def sample mean statistics. Or you give me a sample size and you give me a number of repetitions. And we can see like how many it takes to start looking normal. So let's do all this for like a different amount of dice and things. So group averages, do that for as many repetitions as you wanted, not just like 1,000, whatever you wanted there. And then we want to get the average die value after rolling how many dice? Sample size dice. Let that be up to the user as well. So we've made all those variables, all those parameters. And so we can then make our little table of all those values and draw it, part of the function being called. Sample means that, and we can also just print out some cool stuff. We can say print the sample size. You give a bunch of things to print, it prints them with spaces to separate. So the sample size was this, and then the standard deviation of the sample means is this. That's going to be np.standard deviation of group averages. So that's just a way to control things. So let's say our sample size was 1,000 to make this graph, and we did 1,000 repetitions. So let's do even more repetitions. Let's be sample mean statistics. Let's have a sample size that's even smaller. Let's do just 10. It's not a lot, but let's do a 10,000 repetitions so that we get like a good approximation. So if our sample size is very small, our graph still looks pretty normal if we do a bunch of repetitions. That's quite nice. But just 10, it's going to be maybe a little wonky. So it's going to look a little weird because it's just 10. 10 is not a ton, right? It's going to look different. Sometimes it'll look a little bit odd. It's going to have chunks taken out of it, all right? And so it's not quite normal, but it's approaching normalness, especially when you're doing a lot of repetitions. But if you brought that number down too, then it would look even worse. But let's say we now are going to roll 100 dice and take their average. Do that 10,000 times. This graph is going to start looking a whole lot more normal. It's still got some things, like it's not quite in the middle. It's like plateauing right there. Like on this side, it's a little bit bigger than on this side. It doesn't like fan out perfectly. But it's getting there, right? It's getting there. And then once you do like 1,000, you roll 1,000 dice, it looks even more and more normal. Okay? So that's the idea. This one will take a while though. And so you see that it's starting to do it perfectly. It's starting to look exactly like a normal distribution should. Yeah, you get that. And then also notice the spread. When it's only a size 10 thing, the standard deviation, notice that it's being controlled by the sample size. And so the spread for this one, if it's a size 10, you got like big numbers and small numbers can like throw you off a lot. So you don't have a lot. Like 2 to 5 is the minimax. This one here, 3 to 4. This one here is like 3.35 to 3.65. See how it's getting tighter and tighter when you're doing more and more, taking larger and larger samples. So let's just like print all that out at once. So like our sizes that we used here was, like we used 10, we used 100, we used 1,000 for our sample sizes. And for each of those, call it size. Let's print like size, and then like a colon, and then the population, standard deviation over. Like here was the ideal, right? This is the theoretical standard deviation for a population of that size, and then the sample size that we chose. It's supposed to be the original standard deviation divided by the square root of the sample size. That's sample size, I called it size, 0.5. So here are the theoretical values again. It was supposed to be for 10. The standard deviation was supposed to be this, 0.54. What did we see? About 0.54. It really does hold. For 100, it was supposed to be this, 0.17. We got real close, 0.168. So 2 decimal places, it was correct. And then for 1,000, we're supposed to see this small standard deviation. Theoretically, empirically, what did we see? Yeah, pretty much that. So yeah, the more you do it, the bigger the sample size, the closer it's going to look to be normal. And then also that's going to shrink the standard deviation of your average because you're doing more. It's like you can't like be thrown off as much by a big value or a small value. They're all going to like approach what it should be. Okay? Any questions about that? The central limit theorem. You get normalness out of non-normal things when you're taking the average or you're doing a sum. That's kind of neat. Yeah, so I really don't have much more to say. We can try to knock these slides out today, I think. So this gives us a lot of firepower. This kind of tells us, like, if we want a certain value, like say you want 95% of your values to be between somewhere, you can now connect the idea of a confidence interval as well as like a normal distribution, because we know that 95% of the values that are normally in a normal distribution, at least, are going to be between 2 standard deviations. So we can now connect these ideas and do hypothesis testing and like get values back that we care about. Like we can control things. Like say you wanted a certain result. Like you wanted to predict an average. So central limit theorem applies. We can get normal distributions. And we wanted to make sure that the width of a 95% confidence interval that we generate is going to be between Like it's going to be less than 0.01, let's say. And so like if we were calculating a confidence interval, like this is okay, that one. Because that's within 0.01. But this one's not, because like 0.014, 0.011, I guess. So we can't have that. So yeah, say we wanted those things. Maybe these are like percentage values. Like we want the percentage values to be, we wanted our answer to be within 1% or something. So thanks to the central limit theorem, we know that when we take averages, we get a normal distribution. And we know that a 95% confidence interval, where we know 95% of the values lie, is going to be between two standard deviations from the mean, which is the center. And so now we can connect these ideas because we know something about, like, we have this equation that involves the sample size and we could solve for stuff. It's quite nice. So that helps us choose a sample size. And for some reason, it won't let me undo those red lines under ish. But trust me, it's there. So for example, what this means now, connecting these ideas, is that, all right, when we're making a 95% confidence interval for where we want our values to lie, we can think about plus or minus 2 standard deviations. So that means, in total, 4 standard deviations total, right, away from the center. 1, 2, 3, 4 standard deviations away from the total. We would like the following to be true. We want 4 times standard deviations amounts to be less than the 0.01 that we were trying to like do here. We wanted to make sure that that width, right, was less than that, because then this calculation can take place. Does that idea kind of make sense to us? Because that's how far it would be for center plus or minus 2 standard deviations. That's where 95% of the things are for a normal distributed thing. So we can say this: we want 4 times the standard deviation to be not any bigger than 0.01. And we have a formula for that now. We know that the standard deviation of a bunch of averages is going to be the population standard deviation over the square root of the sample size. We want to make sure that this is true about the standard deviation. We can plug in, we can now solve for standard deviation in terms of this other equation. This one, just like do the replacement, bless you. So once you do that at replacement, I don't care about you memorizing this, but like here's the math. I replaced standard deviation from that equation, so we got 4 times this. All that fun stuff is less than or equal to that, thanks to the central limit theorem. And so what we would like is the square root of our sample size to be bigger than or equal to 4 times the population standard deviation over the 0.01. That was our width that we cared about, right? So if I knew the population standard deviation, I could square it, right? I could square both sides of this equation. I could square it and get a sample size that would be good enough to conclude what I wanted within that 95% confidence range. Does that idea kind of make sense? You can do that in math because we have a normal distribution. But the idea is we're doing this before we take a sample. We're trying to do this before we take a sample to know how big of a sample to get. So we don't know the standard deviation of our population yet, because you would have to have a sample to know that, right? So that's impossible, seemingly. But we can just use the worst case standard deviation. So let's try to calculate the worst case one, because it will always be that one or smaller. All right, we don't know the population standard deviation. We're doing all this before the sample, but if we had a good value for the population standard deviation, we could solve this side, square it, and we'd know how big of a sample to take to guarantee what we wanted to guarantee. So what is the worst case value then for the population standard deviation? So that's like the biggest one it could have been. It's going to, of course, depend on your data. Like if you got heights involved versus percentages. Let's say that we care about percentages. Like that's our running example, percentages between 0 and 1. So we know our minimum is 0, our maximum is 1 for whatever we're trying to calculate percentage-wise. Let me show you a few facts. So first of all, the worst case standard deviation can't be 1, because that would mean that every value was 1 away from the mean on average once you square the deviations. But that just kind of means that the mean was in the wrong spot, if you think about that. Like everything was, that's just kind of saying like, all right, we chose that the mean was 1 when really it should have been like 0.5 or something. So let's just simulate. I can prove that to you with a simulation. We'll simulate a bunch of 0 and 1 values and take the average. So like to calculate percentages, the worst case standard deviation is going to be 0.5. Let me show you. So if I have a bunch of like, I don't know, I'm calculating a percentage of things. Like is it a thing or is it not a thing? Like, am I going to vote for this person or not? So that's the standard. I want to calculate the standard deviation of a population that consists of just zeros and ones, let's say. Ones and zeros is at most 0.5. So let's say that's what I care about. Let's try to calculate the worst case standard deviation. So let me show that to you. We can make a pretty graph. Standard deviation is, and this will be the last thing we do today. It'll be great. Equals, make an array. And then for every value in NP to A range, let's do like from 1 to, 1 to 10. So this is going to go from 1 to 9 now, incrementing by ones. This is going to be, what I want to do is I would like to create an array of I many ones and 10 minus I zeros, so they add up to 10 total. This is going to look weird. So population for this example is going to be np.append. Oh goodness. Is there an easy way for me to show this to you? This is going to take advantage of a weird fact. You don't have to understand what I'm about to do, but there's a np.ones function that gives you that many ones. Like if I want 5 ones as an array, there you go. So I can get a bunch of ones that way, and I can get a bunch of zeros using that as well by saying np.ones. I don't know, they got to add up to 10, so give me 5 more ones and then 1 minus that. That'll give you an array of zeros. All right, so it's just a quick way to do that. So give me I many ones, and give me 10 minus I zeros so that they add up to 10. All right, 10 minus I. There's no real reason to be doing this, but this is what the book tried to do. The standard deviation of all those values is whatever this is, np.append to our standard deviation array, the standard deviation of this particular population. So let me just show this to you. So yeah, I think that's what I wanted to say. So that's a bunch of standard deviations. What I've calculated is a bunch of 0 and 1 standard deviations. Let me make this into a table to show it to you. So what I have done is I've got a population proportion of ones is this. It's just 0.1 to 1 going by 0.1. And then the population standard deviation for a population where there's that many ones and the rest are zeros is what we found there. This is all I'm trying to say. Like if there are 0.1 people voting for candidate X, then the standard deviation is going to be 4. Wait, excuse me. I've done something backwards. I said NP standard deviation of 10, 1. I think I did something wrong. Give me a second. Not ones, I. That seems to be close to correct though. Ones and zeros. Oh, sorry, I forgot to say here np.ones. There we go. That'll make a bunch of zeros now. That looks better. All right, so if you got 1% of the population just like spitballing, we have no clue what's going on. If 1% of the population was voting for the candidate and 90% weren't, the standard deviation of those values, those percentages is 0.3. If 20% of the population was going to vote for the candidate and 80% was not, then the standard deviation was going to be 0.4. And you can kind of see that there's a trend going on where the largest standard deviation that you could have seen for these percentages is going to be 0.5. So that's where it was a 50-50 split. We can do a scatter plot to show that. And so this is just one example of using this idea. Scatter a 0 here. There it is. So you can see that if you connect the dots, this is gonna be continuous, and it's gonna peak right there. So 0.5 is the worst case standard deviation for percentages, 50%. Okay, that is going to be your worst case standard deviation, and so that lets you conclude. Now we can finally plug this in. We had this equation, like what could be the worst case population standard deviation? It's at most 0.5. Now we can square the sample sizes to say that, all right, your sample size should be at least 40,000 to guarantee that you've got this range of things. Does that make sense? Like you can get that thanks to math and the central limit theorem. Like that's a good number. You get as many, take that sample size, and then you are set. You're guaranteed to have what you want. All right. But usually you can also estimate the standard deviation a little bit better. It's usually never the worst case. And so you usually don't have to get that many samples. And so you've seen maybe that like the major polling people, like when an election happens, they take like a little over 1,000, they call like 1,000 people and they get like a decently accurate sample. All right. So apparently you're able to poll like a little over 1,000 people, 1,000 voting Americans, and that's giving you an answer, a legitimate close answer to like what 260 million people, that was our population, would think, all right, with only a 3% margin of error. And so that's because they knew the standard deviation better. They had some more extra math that we don't know about right now. But they're kind of playing this game though, which is the idea. All right. So yeah, that's kind of what I wanted to say. And that is the central limit theorem in action. That was us connecting central limit theorem and like confidence intervals, because we usually care about that. Okay, so yeah, it's a very powerful thing. We'll see it more. We've already seen it before. We just didn't know its name, but now we're happy with it, I hope. Are there any questions about any of that? Because yeah, it's a shorter chapter, but it's packed with a bunch of information. Not a lot of things that you could play around with, but like a lot of very good facts that we'll need for later. Okay, so yeah, with that, that's all that I've got for us today. This chapter, a few assignments depend on it. Project 2 didn't actually depend on it, but like this is where they released it in the Berkeley class. We released it a little bit earlier so that we can keep the schedule properly. But it looks like Lab 8 and Homework 9 are the next assignments that depended on this chapter. This was the last one they needed. So let's go look at our calendar and see when those can be due, and then I'll let you go work. So Lab 8, Homework 9. At least a week from now, at least, is when I want to have them due. So we're in this week. I got to go to November now. So it looks like the next week we have nothing. So that's perfect. So let's do the Wednesday, the 5th. I'll have that homework, the lab due. It's Lab 8 on the 5th. Lab 8, the 5th. And then Homework 9 I'll make due on the 7th. That'll be perfect. And then keep thinking about Project 2. That one's already been assigned. So yeah, those will be our due dates. And I think that's all that I have to say for the day. Are there any questions before I go let you work and do your own stuff? All right. You're experts now.